How'd you guys do on Tuesday without me? Did you stay alive? She was good. Wow, you have a lot of, this is great because the questions are starting to really amp up and be a lot more about all kinds of hard concepts like empty model and what does the little tilde squiggle mean when you're writing R code and things like that. So we're not really we're gonna spend next week talking about models, but I want to say a little bit about the empty model, because the empty model, I was just talking to G actually before class, the empty model is, oh, I wanted to say one thing. Laura, what are you gonna be doing in lab tomorrow?
Hi, I'm back here. Many of you have been wondering about how to see your quiz score and how you did on your quizzes about specific questions. So tomorrow in section, we'll be reviewing every one of the questions, the right answers. We'll go over the free response. You won't actually get handed back your particular answers, but hopefully you'll have an idea of what you said. You can compare against what we're doing. Also, we'll take some of these concepts that you have concerns about that are up there now, and we'll talk about those.
Yeah, so Laura will be dealing with questions, and maybe Adam's going to be there too? I don't know.
He'll be there.
Yeah, okay.
Both these will know which ones to use tomorrow to focus on.
Yeah. And I'll just say about empty model, because you're in the thick of reading about this. How many people have finished chapter 5 already? Okay, a lot of you are still going. So I don't want to spend a lot of time talking about models yet today. But the main thing about empty models is empty models are mainly important because they're what you compare other models to. So when we start building models, statistical models, we need something to compare them to. Like we say, how good is this model? We say, I don't know, what's the alternative? And the alternative, at least in this class, is going to be the empty. The empty model just means the variation you have to explain, even if you don't have an explanatory variable. But once you start having explanatory variables, then you want to start thinking, how good are they explaining the variation? And the only way we can answer that question is by comparing it to the empty model. So that's the reason we need to develop an empty model. But it's a hard concept to get in your head, and don't worry about it too much because the whole rest of the course you'll be thinking about empty models, other models, and so on. I don't think you should ever have to use set seed yourselves. You saw that in some of the R windows. Is that what happened? Yeah. Set seed is a piece of R code we use to start generating a random number. You know, computers aren't actually random, they're actually programmed. So what they do is they simulate randomness. And generally, they start with some number, and that number is called a seed number. And then from there, they have an algorithm to simulate other random numbers. But when you're teaching a class, one of the things you want to do is, like, if you guys try the same code I use, we might want you to get the exact same results as us. And so we'll often put a seed in there and say, start the random process here, so that when you repeat the same code we use, you'll get the same result. And it's just a teaching sort of thing, or a checking sort of thing. So like if you're building models yourself and writing R, you may want to do a set seed because you may want to redo an analysis you did earlier just to check and see if you got it the same way. But in general, you don't have to worry about that. And again, Laura and Adam will go over quiz answers tomorrow in section if you're interested. In general, we'll try to do that every other Friday. And if you need your specific answer, you want to look at it, go to office hours, go to study hall. My office hours are a great place to do that. So, all right. So I also brought another microphone today in case some student wants to talk and be heard. We're going to give it a try. So remind me if I forget to pick it up. What I want to do today is pick up pretty much where G left off last time, and push forward with this idea of randomness as a data generating process. And in particular, we're going to look at how you can use randomness to think about distributions in cases where you're comparing groups and trying to explain variation comparing groups, and also when you're assessing variation in the context of two quantitative variables. So all this, just to put us in context, is still in the explore variation part of the course. When you get to chapter 5, we start building our first statistical models. We start with the empty model. But right now we're still at the explore variation part of the course. But when I say explore variation, I don't just mean variation in your sample. I mean also variation in the data generating process. Because as we've said from the beginning, when you look at a sample of data, you look at a distribution, and a distribution is just that pattern that you see, and you're trying to take that pattern and figure out what does that mean about the way the world works. Is it just that way in my little sample, or is it something that's true about the world? And there's two kinds of thought moves that we can take when we're doing that. One is to look at our data and go, I wonder what that means. And as I pointed out before, you have to take into account all kinds of things, including everything you know about the world, and causality, and the previous literature, and other studies that people have done. But you also want to look at it the other way. You want to say, well, what if the data generating process looked like this? What would that mean for the data? How would the data look? And in particular, one of the most useful ways to do that is to use randomness. So we look at our data, and then we say, well, let's say the data generating process was just random, purely random. Our explanation looks like it's there, but it's only in our data. What if it were just random? What would it look like? And by generating random distributions that are similar to our samples in some way, for example, they have the same data outcomes and they have the same number of subjects and so on, we can begin to put our samples in context. And that's really what this is all about. Now, I can't believe we're almost done with week 3 of a statistics course and we haven't done a single calculation. We haven't even introduced the mean or the standard deviation. So I'm actually a little nervous about it, but I don't think we need it at this point. I think what we're trying to do is get you thinking about data and what it means, and that's what we're going to do. So last time, G showed you these two guys, Bob and Tim, or was it Tim and Bob? And by the way, I looked at your data on the poll everywhere, and you guys were like 80% for Tim on the left. So you really agreed on that. And we reported, I think G reported this study where there were 72 college students, and 61% of them chose Tim. So the results are there. There's 44 people said this guy is Tim, and 28 people said this guy is Bob. And the question is, how do we interpret a finding like that? We look at that finding. So how do we explain that pattern of results? So who can give me an explanation of that pattern of results? Anyone? Who would like to? Don't be shy. What if I said you don't have to use one? How would you explain that pattern of results?
I guess one thing we talked about is that there's maybe certain biases or way that we interpret the image, and people we know in the past with those names kind of influences how we decide which one is which.
Okay, so some sort of past experiences or changing your sort of, giving you different prototype representations maybe of different names and faces, and you guys seem to agree that that's a Tim. Any other explanations for this pattern of results? Yeah, go ahead. Oh, Ralph, I'll give you this. You like the TV reality.
Maybe the name you're given at birth influences how you dress or look or what career you choose.
Okay, okay. Anybody else got an explanation? You have one. No? Come on, you guys, shy. Wake up. Now, that's 2 explanations, but one thing that's true about both of those explanations, and I'm pretty sure you guys could come up with a lot more explanations if I gave you the chance, but none of you yet came up with the explanation of, oh, that's just a fluke. Actually, that's not really true. You just have a small sample, and there happened to be more people who chose Tim, but if you studied everybody in the world, the whole data generating process, it wouldn't be that way. It would be random. It might be split 50-50. And this is a really important point. I brought this up, I think, on the first day, which is when somebody shows you a result like that, your tendency is to come up with the causal explanation. But in statistics, we also have to come up with the random explanation. And that's really what the point was of what you did with G on Tuesday. So the idea is when we're explaining variation, we have to always keep in mind that we want to explain variation in our data, and you can explain variation in data that's true of your data, because does anybody remember what our definition of explained variation is? Yeah, shout it out.
Knowing the explanatory variable would help you to make a better prediction about what the outcome variable is.
Right, that's our definition. If you know the value on one variable, it helps you make a better guess about what the value on the other variable is. And that can be true at two levels. It can be true within our sample. So if you see the difference like you saw there, you know this is Tim, obviously Tim, and the other one is Bob. But you also have to think, is that true in the data generating process? Is that true out there in the real world? So where does the random VGP fit within this model? Because this is something that someone actually asked on the questions that were up there. Where does random go? And why is it important to consider randomness as a possible explanation? See if you can write something about that. Why do you need to consider randomness as an explanation for the distribution of Tim and Bob? How does that help you? It's not showing up? Great. How about now? Yes? Okay. It was doing that on purpose to make you think. In fact, Poll Everywhere has been editing my polls all day. I was coming up with polls for class, and sometimes it would just delete them. I thought, okay, that wasn't a very good question. So I have to come up with another one. While you're doing that, where does it fit in this model? Is randomness an explanation according to the way we talked about explaining variation? How many people think randomness goes in the explained pile here? How many people think it goes in the unexplained? How many people really have no idea? A lot of you just are still writing. That's good. So randomness, we're going to call unexplained. On the one hand, you could say, well, random is an explanation. That's true. But in statistics, it's not an explanation because it's not a variable that we measured in order to look and see if knowing a value on that variable would help us make a better guess about a value on another variable. Because you can't know someone's value on randomness. So randomness is a kind of model, but it's not considered explained. So when you're thinking about how to partition variance up, explained variance is the things that you measure, and unexplained includes two things here. One is just variation in the system that it's real, but you didn't measure it. And the other are what we call variation induced by data collection, and that's where randomness actually goes in both terms, because systems can have random elements. But if they're random, they're never going to be explained by some variable that you can measure. That's sort of the definition of random. So the reason you need to consider randomness is because that's what gives you the context within which to look at the data you got and make some sense of it. So here's my answer to that question. Before you accept an explanation of variation in data, we need to rule out that the pattern could have been produced by a random data generating process. So you don't want to look at Tim and Bob and go, wow, and then, yes, you can think of all your causal explanations, but if it turns out that randomness flipping a coin would have gotten the same results, or could have gotten the same results, you don't want to make a big deal out of it. So this was a slide that G showed you from last time. And what this is, and you guys should remember this, is G created an array with 2 elements in it. One she called Bob and one she called Tim. And then she did resampling from that array. Everybody remember that? So she just said, randomly pick one. It's just like flipping a coin. She also used rflip. You can use that function also. But I like resample. You have your elements, you randomly, it's like flipping a coin, and you just take them. And if you take a sample of 72, and the reason you would take 72 is because that's how many were in the study that you're trying to understand, then what you get is a sense of, oh, I'm going to randomly take a sample of 72, and but those are my real findings at the top. So she randomly took a sample of 72 and got this one here on the left. Then she took another random sample and got that one there. So in this one, Bob was more than Tim. In this one, Bob and Tim were equal. Over there, Tim was more than Bob. So what you do is you begin to get a sense of what the range of different possible samples could have looked like if the process was purely random. In the book, we say over and over again the importance of saying if. I think you've probably already gotten to some of those places. But that's a lot of what reasoning statistically is about. It's saying, well, if it's a random process, what could have happened? And what you can see is a lot of things could have happened. And what you need to do is make a judgment. Could the one that you see in your data, the one on the top, does that look like a member of the family of distributions that all got generated just by random guessing, or a process that simulated that? Or does it look really different? How many people think it looks really different? How many people think it could just fit into the crowd? Yeah, I kind of think so too. Now, later in the course, we're gonna talk about, better ways of answering that question that are more quantitative. Hold on. Question in the front row. How can you?
So, though this sample does look like it could fit into the other random samples we generated, how quickly can we be ruling out the fact that it might actually be random versus there being a possibility that the sample was just incredibly small and that there are other explanatory variables that could explain the data?
I'm not sure I understand your question, but that is the right way to start out. The question is, can you rule out random? Now, if you're just looking at this, you might say, no, I don't think we can rule it out because it looks similar to what we get with random. But eventually, that's the question we need to answer, is can we rule it out? And before we start talking about how to rule it out, I want you to get a sense of why that's important and what you're actually doing when you rule that out. Okay, we're going to take and pursue this a little further. So in that example, you really only had an outcome variable, just Tim and Bob, and just a proportion, really, of people who were selecting Tim versus Bob for the picture. But what we want to do now is move into looking at relationships or explanatory relationships among variables as in the same way, figuring out how we can apply the random alternative to thinking about these. So we're going to use this new data frame, which had a guest appearance in the practice quiz, I think, for chapter 3 or 4, called US States. And I just printed out the head here of US States. So it's the first 6 rows. And take a look at what some of the variables are. So we've got state, Alabama, Alaska, Arizona, household income. That would be the median household income in that state. The average IQ in that state, which is kind of an interesting thing. The percentage of people who voted for McCain in 2008. This is in 2008. Do you even remember who was running in 2008? McCain and Obama. Whoa, those were the good old days, weren't they? The population of the state, the average 8th grade math score on the NAEP, which is a large government study that looks at math scores across the country, math achievement. The percentage who graduated high school. I like this one. The percentage who eat their 5 portions of vegetables each day. The percentage who smoke. The percentage who competed in a physical activity in the last year. Those percentages look pretty high. I wonder what they really mean by that. Percentage who are obese, percentage non-white, percentage heavy drinkers, and who the state went for in 2008. Was it McCain or Obama? So I took 5 vegetables, and here they are. They're green, as you can see. And just to model what I've been telling you from the beginning, the first thing I'm going to do is look at that distribution, right? Of 5 people, percentage who ate 5 vegetables. And I want you to look at that distribution, that histogram. And here's another question, I think. What do the numbers on the y-axis mean? And I'm going to show it to you again. Is it up? Okay. What do the numbers on the y-axis mean? By the way, this is an example of what I mean by cumulative as you're going through the course. Every now and then I'm going to ask a question that you probably know the answer to, but kind of brings you back a little in time. All right. Oh, come on. Let's get some more votes. What is the number on the x-axis, y-axis? All right. Is everybody ready? Oh, no. All right. Let's go back and look at it. I think I said you can't change your answer on this one. But it turns out percent of residents in each state is not correct. Okay? First of all, what is every row in this data frame? Who knows what every row is? A state. How many rows are in the data frame? 50, exactly. So whenever you do something like count, in a histogram, you're counting how many cases are within a certain range, okay? So for example, on the x-axis, you have the percentage of people in the state who eat their 5 vegetable servings every day. So if you look down at the bottom and you look down on the left where you have that little clump, you have 15%. That means there are some states where only 15% of the people eat their 5 helpings of vegetables. And on the y-axis, the count is the number of states that fall in that range. So this is incorrect. B is the correct answer. And C is also incorrect. So this is important. This is something you might be able to go over a little in section because this kind of thing will definitely be on it. But the key is whenever you're looking at a histogram, the y-axis is either going to tell you how many are in that category of scores that are defined on the x-axis, or it's going to tell you the proportion of those, like the proportion of states that are in that category. Somebody I noticed asked the question, when would you use a relative frequency and when would you use the frequency? And whenever you're looking at just one distribution of one variable for one sample, which we have here, it doesn't really matter. You can look at the number of states, so you can say, oh, there's like 5, 10, 15 states where 22 to 24% of the people are getting their vegetables. Everybody see that? Actually, these percentages are just really low in general. We don't eat a lot of vegetables. Or you could look at the percentage of states where that happens. You're going to get the same picture. But if you're comparing histograms across different groups, and you want to say things, for example, do they eat more vegetables in the southern states or in the northern states, then if there's a different number of states in the north and the south, you're going to want to use a relative histogram, because otherwise it'll be hard to compare. And somebody else asked, what's a density histogram? And a density histogram is really just like a relative histogram, but it's like some super sophisticated way of calculating relative frequency that you don't need to know about, and you probably should never know about that. Okay. Here I made a histogram of 5 vegetables, and I did it separately for states that went for McCain in 2008 and states that went for Obama. That's the pajamas. Okay. So what can you see here? What does it look like? Just take a look at these histograms. So on the top, we have the states that went for McCain. On the bottom, we have the states that went for Obama. And where does it look like, on average, they sort of ate more vegetables? In Obama states or McCain states? Who says McCain states? Who says Obama states? Yeah, it looks that way to me. Review our definition of explaining variation. So could we say that Obama versus McCain state helps us to explain variation in percent of population that ate their 5 vegetables? Does it help to explain the variation? Does knowing whether a state went for Obama or McCain help you make a better prediction about their likelihood of eating their 5 vegetables? How many people think it does explain it? How many people don't think it explains it? Tell us what you're seeing. And where do you see randomness?
Because there's like the same amount of states that like that middle one.
Yeah.
Both states are the same. So,
Yeah.
those are the states, and the lower amount of vegetables is for the McCain states. It just seems like random.
Okay. Random, it's important to distinguish between random and variation. So, yes, I agree with you. There's variation all over the place. And remember, when we're looking at distributions, we're looking for patterns of variation. So, I totally agree with you. There's a lot of variation. On the other hand, randomness can happen even if there's not a lot of variation. So, we want to disassociate those two concepts. And that is something we want to know, is whether it is random. But it does look like, if you're just looking at the pattern in your data, that there's more vegetables being eaten in Obama states. So if that's the case, and if knowing it, to say a variable explains another one doesn't mean it explains all the variation. It just means it helps a little bit, just a little bit. So if I said to you, I'm going to randomly take a state that went for Obama, and I'm going to randomly take a state that went for McCain. I'm going to hide them behind my back. Which state ate more vegetables? Your guess would be the Obama state, right? And you could be wrong. You'd all admit that you probably could be wrong, but you think if you had to bet on it, you'd bet on the Obama state. And that's really all we mean by this. Now, the question was, does what president you went for in 2008 explain variation in 5 vegetables in our data? Does it explain variation in the DGP? How is that question different? I'm going to need a microphone for this. How is it different to ask, does it explain the variation in the DGP? How would you think about that question differently? Someone has a thought. I'm saying my thoughts. Who's got a thought? What is the DGP anyway? It's the data generating process. So if we're thinking about, does it explain? Yes. Hold on, use the microphone. Otherwise, not going to bring it.
I don't think you can determine directionality in terms of which variable is explaining which variable.
Okay, that's a really good point. You can't determine directionality or causality, but causality aside, causality isn't our definition of explanation in this class, is it? It's just, does knowing a value on one variable help you make a better guess about another variable? So it could be causal or not causal. If it helps you make a better guess, we're still going to call it an explanation. But this is just a sample. This is just a sample. So the question is, this sample was produced by some sort of data generating process out there in the world that we can't see, and we don't want to be misled by our data. It's just like in the case of Tim and Bob. Just because more people chose Tim, we don't want to assume that that's actually true, that there's a bias towards choosing Tim. We want to say, well, maybe, could it be just random? Let's look at it and see if it could be just random. Write a model statement in your notebook. You know, like the words we've been writing, not the notation, but just the words. How would you write a model statement to describe the question that we're asking? Propose what the model would be. Who wrote one? Just quickly. What'd you write? Vanessa? Yes. Yeah, 5 vegetables equals Pres 2008 plus other stuff. How many people were sort of heading that direction? All right, I want you to be heading that direction. And what does that mean? Does it mean, oh, if you want to know how much vegetables somebody ate, you just add up their presidents and a little other stuff and voila, you have, no, it's not like that. It's not a formula. It's a representation of the relationships. It's a representation of what we're seeing in our data. All right, so here's a question I want to bring up, because hopefully some of you are confused by this. And that is, in this data frame, we have a sample of states, American states. Is that a random sample of states? How do we choose which states to put in our data frame with 50 American states? Anybody got an idea? That might be the order we put them in, but how do we know which ones to choose? Yeah? All 50 states. So in a lot of statistics course, people say, well, you have a sample and you have a population. But in this case, it almost looks like the sample is the population, because there's no other states we could have chosen. But this is why the distinction is really important between data generating process and population. Even though we're only can study 50 states, it doesn't mean that we couldn't still have a biased sample. Because the sample that we're really interested in is the sample that gives us a picture of the data generating process. So you've got to think of it, and again, there's so much hypothetical thinking in statistics. You've got to think, oh, there's a process out there that generates a state that has certain characteristics and a relationship between two variables. And so far, it happens to have generated these 50 states, but there could be a whole bunch of other states that just didn't happen to get generated randomly. Isn't that a weird way to think? Very weird. Like, there could be an infinite number of states, but we only ended up with 50. So that's the way to think about the data generating process. So the data generating process is the process that produces the population at any given time. So think about that. But also realize that the population keeps changing over time, just because everything's always changing. It might be that in 100 years, there will only be 20 states, or there might be 1,000 states, or there may not be states. So think about data generating process and population as going together. And in some situations, it's more useful to think about the population. Like if you're doing a political poll and you want to predict who's going to vote for who for president, it makes sense to think about a sample from a population because you're trying to predict from the population of likely voters, who are they going to vote for, and you take a sample. But if you're studying something like the 50 states, then you want to think more in terms of data generating process. All right, so now let's go on and think about how we would simulate a random data generating process. And what I'm going to do is go through and do this in the sandbox. And I'm going to let you guys pull up that sandbox if you want and follow along. Just type in as I am and see what you get. So you get a little bit of practice on this. So bit.ly/100 capital A dash capital R. And I think you guys went there in your last lecture. And let's see if I... Okay. Now, just again, I'm modeling the way I went through and did this literally yesterday. But the first thing I'm going to do, I don't know if you can read this, honestly. Can you read that? All right, I'm not even going to do it. All right, I'll take you through on slides. But you can still type these things into your... You can still type these commands into the sandbox, even though I'm not going to do it up here. Okay. So the first thing I did, and if you want to type this in and follow along, please do, is I decided I'm not going to mess up my data frame, US states. And this is something I often do. Like, I'm going to be changing variables around and randomizing them and so on. I don't want to mess up my data frame. So I'm going to make a new data frame. And what did I call my new data frame? How do you like my name for my new data frame? It's good. Yes. It's a very good name. Okay. And I say select paren US states. That's the name of the data frame I'm working with. Comma 5 vegetables, comma pres 2008. So why am I doing that? That's the relationship I'm interested in. So what is this command doing? Who can tell me what this command is doing? You guys got to have some answers. Who can tell me? What's this doing? All right. Thank you.
All it's doing is, from the US states data frame, it is picking out only 5 vegetables in Pres 2008, so you can only focus on those 2 instead of being bothered with all the other ones.
Good.
So it'll just list.
Good. And what about after that? Head new data.
It just shows the first 6.
And how many cases do you think are in my whole data frame?
50.
50. And why do you think 50?
Because it's 2 states.
Okay, so when I use select, I didn't reduce the number of states at all. I just reduced it down to the 2 variables I'm interested in. Okay, so the next thing I want to do is I want to see if I can use the shuffle function, which I think you've seen before, in order to randomize the relationship between who the state went for presidentially and the percentage of 5 vegetables. Now, what I'm doing in essence is we saw in our data a relationship. We saw that the vegetable distribution was a little bit shifted towards more vegetables for the Obama states than it was for the McCain states. And what I want to do in order to check out whether random processes could have produced the distribution I saw is I want to break that relationship so it's totally random. And one of the techniques I can use for that is to just shuffle Obama and McCain. So what I did is I wrote this code, and you can write this if you want to. New data, $pres 2008, shuffle. Okay? What am I doing there? Making up, what am I creating when I start this command here? Who sees what I'm making? I'm making something that didn't exist before in this data frame. What am I making? New states? What am I creating? Parsia.
You made a new shuffled variable.
I made a variable, okay. I made a new variable called Pres 2008 Shuffle, and how did I get that variable? I took new data Pres 2008 and shuffled it. So look at what happened when I did this. And then I headed it out. So in the first column is the percentage who ate the 5 servings of vegetables. The next column is who the state voted for. That's actually who they voted for. That's the one I already showed you the data for. The next column is shuffled. So read down those names. Obama, McCain, Obama, Obama. And compare it to the unshuffled one. That's all that does is it shuffles that variable. And by shuffling that variable, it means if there's still a relationship between those two, it should be broken. This should totally break that relationship. I also did a tally. And I should have done a tally before. But here's a question for you. I got 22 McCain states and 28 Obama states in my shuffled variable. Do you think, how do you think that would be in the unshuffled variable? What do you think those numbers would be if I did a tally in the unshuffled variable? The same. Why would it be the same? Here.
Because you would have the same number of states participating and they only have one value for McCain or Obama.
Okay. It's different than Tim and Bob. In Tim and Bob, I made a new vector and I called it with 2 elements, Tim and Bob, and I did just randomly pick one. Each had a 50-50 chance of being picked. In this case, I'm not randomly picking Obama or McCain and giving each a 50-50 chance. I'm just randomly shuffling the values of Obama and McCain. So I still have the same number of Obamas and the same number of McCains. It's just that I've shuffled them around so they're all linked up with different states. Okay? Anybody have a question about that? Does someone have a question? I'd love for someone to ask a question. Yes. Love for you to ask a question. Yes.
I have more of a general question. Does R just save like the U.S. states data frame? So if we just like typed in head U.S. states, would it just come up with all of them, or is it like preset by like you guys?
Well, it's preset by us guys. And the reason it's preset by us guys is because there's probably 100 million data sets in the world. So we only have a few that we've brought in. But one of the things we're not going to really spend time in this class teaching you how to go find a data set and bring it in, but it's not hard. That's pretty easy. And once you get it into R, it's going to save it. But here's another thing. Once you import a data set into R, it's going to be in your version of R. And this doesn't so much apply to the data camp, but when you install your own R. And then you can screw around with that data set. And if you really mess it up bad, you can just delete it and re-import it again. But all the work you did won't be done. It'll be the original data set. So like if you went and created a variable called Pres 2008 Shuffle, that wouldn't be there, obviously, if you re-downloaded the data set from its original source. But if you saved your R code that you used to create it, you would just have to push run one time and say, redo everything I did, and it would do that. So that's the way that works. Okay. What will happen if I run the same code again? So look at the code at the top here. This is exactly what was on the previous slide. So new data Pres 2008 Shuffle is shuffle new data Pres 2008. I ran it once. I got these results. I'm going to run it again. And here is the question. Which of the following will change if I run this code again? There's 5 choices. I'm going to run the code again. I'll show you the code while you're thinking about it. So I'm making a new variable, Pres 2008 shuffle. By shuffling Pres 2008. And now I'm going to run it again. What's going to happen? What is going to change? And what is going to stay the same? Yes?
What's the point of using this shuffle? What are we trying to get out of it?
The reason we're using shuffle is we want to take the distribution, and I'm going to say this over and over probably for the next 8 weeks, and you just have to gradually understand it. But we want to take the distribution that we found when we actually gathered data on Obama versus McCain and percent of population who eat vegetables, and we want to say, what if those variables were generated by a completely random process? What would the distribution look like? So we're trying to get a distribution to compare our distribution to. The reason we want to compare our distribution to a random distribution is we want to say, could we have gotten the distribution we got if the true DGP were just random? That's the crux of the matter. So it's just random. Could we have gotten the distribution we got? We all agreed that it looks like in Obama states, they eat more vegetables. What we're trying to know is that really the true data generating process, or is that just an accident of the sampling that we just did? All right. Which of the following will change, including none of the above? And yeah, that's correct. Only the President 2008 shuffle column will change. Why is tally not going to change? Tally is not going to change because we haven't changed the number of Obamas and McCains. It's always going to be the same number. We're just shuffling them around. Okay, so I did it. I ran it a second time. And if you look at these two tables, you can see that they all look the same. Look at the bottom. That's the tally. So the tallies are the same. The first 6 states and their average numbers of vegetables are the same, right? Who they went for in the 2008 election is the same. You can't change that. But where we shuffle them, that's what's different. So every time I run this command, it's going to shuffle them again. And I'm going to get a different sequence of Obama and McCain, but I'm still going to have 22 McCains and 28 Obamas. Okay, so this is a histogram of my first random shuffle. So take a look at this. And in your mind, try to bring up the green one that we looked at before, and just think, do you see the same relationship in this histogram that you saw in our data distribution? Remember, in the data distribution, you all agreed that knowing who the state went for helped you make a better guess as to their likelihood of eating vegetables. Do you see that relationship in this histogram? How many people can see the same relationship here? And how many people think it's not there or it's been reduced? Who sees the same relationship? Are you guys looking? Who thinks it's not there or it's been reduced? That's what I think. I don't see, it seems like more overlap, but it's not all one way. As you pointed out, saying it looks random, it still looks random, but it looks more random, okay, in the sense that you were talking about. So you don't see as much cross-group variation. So what we're going to do is, that's the distribution I show you, and then I'm going to run it again. And I get that. Why does this look different than the first one? Because I reshuffled it, okay? There's another one. You can see, remember the 3 states out on the left-hand tail? They were there in the beginning, they're there all the time. But what's changing is, randomly, sometimes they're getting put in the Obama camp, and sometimes they're getting put in a McCain camp, and you can see, like, on the first pair of histograms there, all of the low vegetable eaters got put in McCain, but if you look over at the next one down here, only one of them went to McCain and two of them went to Obama. Is that right? No, two went to McCain and one went to Obama. Okay? And this is the kind of thinking that we're going to do a lot of, and in different ways as we begin to develop models. But if you look at this, this is the family of distributions that we get when we when we model the data generating process as completely random. We get this family of distributions. And the question is, and there's the original data distribution, does the data distribution look like it could have just been part of the random family, or do you think it looks like it could be different? So how many people think, apart from the color, by the way, because that does make it look different, but how many people think the data distribution in the upper left-hand corner looks like it could just be generated randomly as all the others were? How many people think it looks different? I think it could go either way, but I kind of think it looks different. I don't know for sure, and you don't really have a technique yet for helping you make that decision, but I think it looks different. It looks a little less overlap, but it's not wildly different. It's not wildly different, okay? And that's why when we observe something in data, we always want to be considering, well, what would a random process have done? Yeah. So, oh, everybody chose Tim. Well, what would randomly happen? Would everybody choose Tim randomly? Maybe sometimes they would. How likely would that be? Yes?
So I'm just a little confused still on the goal of if it could be random. I understand the idea of trying to compare random processes to the like original data that we actually collected, but if we get to this point where, let's say we decided that it could be a random process, I don't really understand the next steps or like why we would do this.
That is a great question. Why would we do this? So we're going to be doing a lot of this, but for today, there's two possibilities. One is you look at it and you go, wow, that's really different. There's no way the data we observed could have been generated by a random process. If that's the case, that means we've actually demonstrated that in the DGP, there is this relationship between who you voted for president and how many vegetables you eat. If, on the other hand, we look at it and we say, you know, yeah, it sort of looks like there's a relationship there, but so do a lot of these others. They all look kind of similar. If that's our decision, then we're going to say, you know what? We jumped the gun. This whole Obama vegetables thing, it could have just been random. And in science, when you're trying to explain things, you usually go down to the simplest explanation. Random is a simpler explanation than, oh, there's a process that's causing Obama voters to eat more vegetables. That's a really complicated theory compared to just, oh, it's just random. People vote, people eat vegetables, and you're not going to be able to establish any relation. So if it looks really different from random, then we're going to take that as evidence that there's a real relationship there in the DGP, not just in our sample. There's clearly a relationship in our sample. It's not hard and fast. There's a lot of overlap. But you can sort of see a difference, the distribution. Remember, we talked about distributions. We don't want you to look at specific states. We want you to look at just the overall pattern. And the overall pattern is, yeah, there's a relationship there in the overall pattern in our data. The question is, can we say that it's there in the data generating process? And based on what we see here, you could go either way. And we're going to come back to this example later and figure out, when we learn more tools, how we can make a better judgment. This is the point. This is the main point of this, is before we accept an explanation of variation in data as true about the DGP, we need to rule out the pattern could have been produced by a random EGP. I think I repeated this slide a few times. And I'm going to post these slides, but it's still good to write it in your notebook. This is really important. This is one of those statements, though, if you memorize this statement every word, it's not going to help you unless you really understand it deeply. So you got to think about this. And don't be embarrassed to keep asking the same question over and over again. Because that's how I figure all this stuff out. Is you ask, you think you understand the answer, but then you go sit down again and you go, what? I don't remember what I even thought. And then you try it again, and eventually it makes sense. All right, in the last 15 minutes, I want to see if we can take this exact same approach that we use for evaluating a pattern of relationships between two groups. So Obama versus McCain, explaining percent of vegetables, and see if we can extend that to quantitative explanatory variables. So to do this, I went back and looked at some of the variables here in the US states data frame. And I started just generating some scatter plots to look at the relationships. And I don't think I made this into a poll everywhere question. But would all of you know how to write the R code to produce this plot? This is the kind of thing that couldn't even be on next week's quiz. This is obviously GF histogram, right? I mean, what is it? GF, who said it? GF plot? Point, yes, point. GF point, and what does that little tilde mean? Remember, which would go first? Would it be 5 vegetables tilde physical activity, or physical activity tilde 5 vegetables? 5 vegetables tilde. So the tilde thing, and that's going to come up more and more as we start using the LM function in R, it's basically just, there's no reason we have that little squiggle. It could have been any squiggle, or it could have been an X, it could have been a lot of things, but it's a squiggle. And in general, though, before the squiggle are things we're putting on the x-axis, and after the squiggle are things we're putting on the y-axis. So if you think about, I'm sorry, before the squiggle y-axis, after the squiggle x-axis. If you think about the word equations you've been writing, what would be a word equation for this? 5 vegetables equals physical activity plus other stuff, because there's a lot of other stuff there, right? And so LM sort of works in the same order. So you've got your outcome variable on the left, and then your explanatory variable next, and then other stuff is there because there's variation. What would this graph look like if there were no variation in 5 vegetables? If we had time, I would ask that as a poll everywhere. What if there were no variation in 5 vegetables, but a lot of variation in physical activity? What would this look like? Anybody got an idea? Yes? Like a horizontal line, right through probably the average of 5 vegetables. If there's no variation, it would sort of be there. And if there's no variation in physical activity, it would be a vertical line. And what if there were no variation in anything? It would just be a dot in the middle. And would we be doing statistics? No. But would that ever happen? No. Do you see physical activity explaining variation in 5 vegetables in this data? Remember our definition? I can't remember what slide. Here's our definition. Knowing an observation's value on the explanatory variable helps you make a better guess about that observation's value on the outcome variable. So, does physical activity appear to explain whether you eat 5 vegetables? How many people think it does? How many people think it doesn't? Okay. I'd like more of you to just keep thinking one way or the other. But yeah, it looks like it. If somebody gets a lot of physical activity, those states seem to be up higher on the vegetables, and states where you get less seem to be down lower. Oh, here's another one. Physical activity in smokers. Percentage of smokers. Does physical activity appear to explain smoking? Yeah, it's sort of the opposite. Now, being high on physical activity means you're less likely to smoke. But do these things kind of fit with your sort of view of how things all work together? Yeah, they make sense. We're always trying to make sense. Physical activity and being obese. Percentage of people who are obese. Yeah, I think that looks like a relationship. Now, I just plotted this one, but I can't figure out why. But physical activity and 8th grade math, average performance in 8th grade math. Does that look like a relationship? Can anybody think of like a causal theory that would explain this? Hold on.
I mean, exercise is proven to improve your brain functioning, so they could have done better on their math.
So maybe exercise literally is improving your brain functioning, and so if more people have higher brain function, then anybody got another idea? Yes.
More physical activity could indicate a greater like socioeconomic middle class, and therefore more resources for education.
That's interesting because you're positing another variable that we didn't measure that could be correlated with both physical activity and 8th grade math.
Physical activity can lower stress, which could improve your concentration and you can do better in math.
Yeah, that's great. Physical activity can lower stress. Anybody else? Gosh.
If you're involved in physical activity, you can be in sports, and usually sports require a certain GPA and doing good in school.
So if you're in sports, you have to have a certain GPA, and if you have a higher GPA, you have a higher math. Boy, this could go on forever. But what is the one that nobody mentioned so far? Random. It could just be random. Like, there's so many variables in the world, you could plot them all against each other. Maybe they don't mean anything. Maybe it's just random. So how are we going to tell if this is random? It's not random in our data. The pattern is in our data, but is it possibly random in the data generating process? So, can we use shuffle the same way we did before? Before, we shuffled Obama, McCain. So if it said Obama, Obama, McCain, McCain, we did a shuffle, it might say Obama, McCain, McCain, Obama. Can we use shuffle the same way? Yeah, we can use shuffle the same way. Take a look at this code. So we take US states, and I'm making a new variable called PhysAct shuffle. So I'm going to take my explanatory variable, and I'm just going to shuffle it. The beauty of this is it's actually using my data. So I have my data set, it's got 50 states, each one has an 8th grade math score. I'm not going to mess with that, but then I'm going to take their score on physical activity, and I'm just going to randomly shuffle those same numbers so they're all matched up with a different state than they originally were. So you can see how conceptually I'm breaking the relationship. There was a correlation in my data table between being high on math and high on physical activity, but I'm totally breaking it. I'm saying we're just going to make it random. And if I do the head of that, I can see that I have 8th grade math scores. They go 262 down to 280. This is just the first 6 cases. And then physical activity, 70, 79. And then on PhysAct shuffle, I've got the same numbers, just reshuffled. Yes?
Aren't these sampling through different populations that's sort of comparable? Because assuming that not every single person that was sampled was an 8th grader, so you're sort of comparing like all the people in a certain state with their physical activity and just the 8th graders in that state.
Well, what are we sampling here? What are we studying? Are we studying 8th graders? Are we studying people? Are we studying, what are we studying? I mean, this is really a critical, that's a great question.
I think we're trying to study the relationship between the states and, well, I guess the relationship between the math score and the physical activity level for each state to see what the relationship is. But actually, just
Well, what we're studying are states. But you have a really good point, because even if you found a relationship across states, that doesn't mean the same relationship would be there if you just went and studied 8th graders. So these characteristics are characteristics of states. So it's not like it's different populations, it's a characteristic of the state. Like, state will have other characteristics too, like a GDP and a main industry and an average income and all these other characteristics. Another characteristic could be, variation in income from min to max. There's all kinds of things, but these are characteristics of states. 8th grade math is just a characteristic of a state. But anyway, so we shuffled it. All right, here's a question, the last Poll Everywhere question. If you run FABstats, remember FABstats? On physical activity and physact.shuffle, what would be different between those two? Each separately, FABstats. So remember, physical activity is the actual measured variable, one for each state. Physact shuffle is the shuffle of those numbers. So now we're going to run FABstats on both those variables. What's going to change between those two? This requires you to really think about FABstats. Remember FABstats? Well, there is a median, but there also is a mean listed for FABstats. But median would have been better. I hate to put mean in because we haven't studied. But FABstats does put a mean in. FABstats has the minimum, the maximum, the Q1, the Q3, the median, which we could call the Q2. All right, hurry up, we're running out of time. I want to get to the punchline.
If it's just shuffling it, I think it wouldn't really change anything.
Someone asked if they could write jokes into the beginning questions. Yes, you definitely can, but it has to be funny. So far, all the jokes I've seen.
Think about that. Not changing anything.
Okay.
All the questions are like that. The answer no.
None of the above. That's the correct answer. Although all of the above, a third of you got it. This is something we need to think more about. Here's the FABstats. The FABstats are going to be the same because even though we shuffled them, the numbers in that variable, in that column, they're the same numbers. So they're going to have the same minimum, the same maximum, the same median, the same mean, the same Q2, the same Q3, Q1. All that's going to be the same. All right, so here's the data that we observed. And I ran the shuffle, and I got this. So I got this, where we all saw that relationship. And then I ran a shuffle. And do you see the relationship anymore? It seems to have gone away. So I ran 6 more times. And it looks, in this case, like a very different pattern. It really does stand out. The data that we observed in our sample and the result of the exact same data where we randomized the connection. So in this case, to get back to your question, you'd say, that might be a real relationship. Because if it were just random and we kept spitting out samples of size 50, you're not going to see that relationship. All right. Sorry you got some wrong answers today. Study hard. See you next week.